Go ahead and get started. If you have questions or comments that you want to make, use the Q&A function. So as I go through this, I won't try and answer questions right away because we could get bogged down doing that. So I'll hopefully leave some time at the end to answer some of the questions. If not, then we have the questions, and I respond to those and they'll be sent out via email. Also, this session is being recorded and it'll be made available, I think through YouTube. I'm not sure about that, but Georgetown will give you that information. And then also, I will make the slides available, and Georgetown will also send the slides out to everyone who is registered. So our topic for today is power analysis and sample size estimation. Let me give you a bit of an outline here. If it'll go to the next slide, there we go. So to begin with, I'm going to take some time to review statistical decision making, because that's important to understand that when we talk about estimating sample size. And then so we'll talk about what statistical power means, how we estimate sample size. And I'm going to do this for some relatively simple examples, general linear models like t-tests. We'll look at time to event analysis, survival analysis, then equivalence or non-inferiority designs. We'll spend a few minutes talking about sequential analyses, and then power and sample size for clustered data. Then I want to end up by talking about the information that we need for a power analysis, and then talk a little bit about the abuse of power. I borrowed that from a article that I have in the references, but it's fairly common to see power or the concept of power misused in research studies. Okay, so begin with, obviously, when you plan a study, you're going to be required to estimate the sample size that you're going to need. And what do we mean by needed? Well, it's needed to demonstrate that the result is not likely due to random sampling variability. And I'll go over this in more detail, but we're not getting sample size to determine whether the results are important or meaningful, but it's related to the concept of statistical significance. And probably the main quantity that we're going to need is what's known as the effect size. In other words, what is the difference in the statistic that you're calculating based on your design between treatment groups, or maybe you want to look at demographic differences, but we need to specify some sort of effect size. And this effect size comes from, or can come from different sources. Maybe it's clinical experience. What you would like for the most of the time, though, is to estimate it based on prior studies. Or maybe you've done a pilot study to get an idea of the difference that you're, or the differences that you're expecting or hope to see. And kind of a last gasp analysis, if you have no idea of an effect size, then we can do some best guess scenarios, which I'll give an example of at the end. Okay, so for estimating sample size, obviously we need to know the design and then what the statistical analysis is going to be based on that design. So we're going to need to know outcome variables. If in the case of non-randomized studies, you might have a number of covariates that could be confounding. And so you may need to consider those and take those into account in determining sample size. If you want to look at interactions or subgroup analyses, then those are going to require a larger sample size. And the thing is that most studies that are published don't, even though they might do subgroup analyses or say something about interactions, they've not really powered their study to look at those. So even though they present results and even p-values with subgroup analyses, they're all, for the most part, underpowered. And then the concept of interim analyses. So in randomized trials, often the investigators want to take a look at the results before the study is finished. And so we refer to these as interim analyses, and this affects the both the sample size as well as the alpha error rate and the beta error rate. So let me do a review here of hypothesis testing of statistical analysis. So we start out with our research hypothesis. So this is a statement that you believe to be true about your population of interest. And so as we mentioned, we've stated this as an effect. For the most part, you might want to look at differences between treatment groups or treatment and placebo groups or standard of care. And then from a statistical standpoint, we when we do the statistical analysis as well as the power analysis, we have what's known as the null hypothesis, and this is straight contrary to the research hypothesis. And the well-known p-value that you see in research studies, that's the probability that the observed effect could have been obtained if the null hypothesis were true. So when we do statistical analyses, we're always going to assume that the null hypothesis is true. And then we're going to calculate a probability that the research results or the observed effect could have occurred just by chance or random sampling variability if the null hypothesis was true. So we're going to, in our statistical analysis, obviously we're going to test some or calculate a test statistic. And that is a value computed from the data. And then that's compared to a known distribution of what would be expected if the null hypothesis were true. And a simple statement of this, so it's a little more complicated depending on the statistical analysis, but basically it's the observed minus the hypothesized, or what you observe minus what you think you would hope, or what you had hoped to observe, divided by the standard error, the difference. And so the numerator is our effect, and the denominator is a measure of the variability of the sample statistic sampling distribution. And sampling distributions are, for example, the normal distribution. We'll talk about that, the T-distribution, chi-square distribution, binomial distribution. Those are all sampling distributions, or what we call sampling distributions. And so what we want to do is we want to reject the null hypothesis. And so the logic of that is that if we can reject the null hypothesis, then we gain support for the research hypothesis. So if the p-value is small, then the probability that the effect occurred because of chance is small. What a p-value is not is the probability that the null hypothesis is true, or the research hypothesis is true, or the null hypothesis is false, whichever way you want to say that. But it's a conditional probability that the research results are due to chance, assuming that the null hypothesis is true. And then, as I mentioned, if the null hypothesis can be rejected, then we infer that the research results were due to something else. Obviously, we want to infer it was due to our treatments or some particular patient characteristics. If the p-value turns out to be large, that is, we get non-significant results, traditionally that's greater than a p-value of 0.05, then we can't reject the null hypothesis. And the only thing that we can really say is that we have no evidence that the effect occurred as a result of anything other than chance. And that doesn't necessarily mean that there isn't an effect, that there isn't a true difference in the population, but we haven't been able to detect it with our sample size. So sometimes if we can't, if our p-value is greater than 0.05 or whatever you set it at, it's sometimes referred to as accepting the null hypothesis, but failure to reject would be the preferred terminology. So probably most everyone who's taken a statistical course has seen this 2x2 table here. So what we have here is the true situation in the columns, that is, whether a difference exists in the population or there's no difference in the population. And the rows then are the conclusions that we make from our statistical test, whether we conclude a difference exists or there is no difference. And so if we, based on our statistical analysis, say that there is a difference that exists in the population, but in reality, no difference exists, then we've made what's called a type 1 error. And the probability of this we refer to as the alpha error. Then if there is no difference in the population, and we conclude there is no difference, then we've made a correct decision. The probability of this is just 1 minus alpha. On the other hand, if there is a true difference in the population, but based on our statistical test, we conclude that there is no difference, then we've made what's called a type 2 error. And the probability of this is the beta, is what we call beta, or the beta error. And it turns out then that in the situation where there is a true difference in the population, and based on our statistical test, we conclude that a difference exists, then that probability is 1 minus beta, and this is what we call power. In other words, it's the power of our statistical test to detect a true difference in the population. I'll just, someone asked in the chat here about the slides. Yes, the slides will be made available after the session. I'll send those out, and the folks at Georgetown will email the slides to everyone who's registered. Okay, so power then is rejecting the null hypothesis when it is false. So we can actually increase power two different ways. We can increase power by increasing the type 1 error rate. That is, we can make the error rate bigger. So if 0.05 is, so that's sort of the standard type 1 error rate that everyone uses, but if we make it 0.1, then we can increase our power. However, nobody really wants to do that because the type 1 error is really the most serious error. Or at least is considered the more serious error. So let me illustrate this in pictures rather than in words or in the table that we looked at before. So we have our two distributions here, our null distribution and what we call our alternative distribution. The null distribution is referred to as a central distribution. The alternative distribution is referred to as a non-central distribution. And so you can see that if we focus here on the null distribution and we look at our what we've decided we want to be our alpha error rate here, if our p-value falls in this region, then that means that there's a small chance that our results really belong to the null distribution. It's more likely, at least it looks like, that it's part of the alternative distribution. And so this, from our null distribution, this is our alpha error rate, or where we get our p-value from. Okay, so then if we focus on the alternative distribution, then this area to the left of our cutoff here is the beta error, or the area under the curve that is the beta error. In other words, if we get a p-value that's larger than what we wanted, that we had hoped for, then it would fall somewhere in here. But if this is really part of the alternative distribution, then we've made the type 2 error. Even though it's might be more likely that it's part of the null distribution, but in reality, it's part of the alternative distribution. The area here to the right in our alternative distribution, this is obviously then, if this is beta, this area over here is 1 minus beta, and this is the power of our statistical test. And so you can see that what I mentioned before, that if we increase our alpha, in other words, we make the alpha error rate larger, we move this to our vertical line here to the left, then you can see that power is going to increase. But we don't really want to do that because we want to keep our type 1 error rate small. So let me give an example here that if we actually knew what was the true situation in the population, how this would work. And so I have just two group doing a 2-sample t-test here. So X1 and X2 are the means of my 2 samples. S1 and S2 are the standard deviations, and I've made them equal to make it easier to calculate here. So this my standard error of the difference is just the standard deviation here times the square root of 1 over the sample sizes, 1 over the sum of 1 over the sample sizes. And so we're going to assume in this case that our sample size is equal to 10. So if we calculate this out, then our standard error here, our standard deviation of the sampling distribution, is equal to about 5.4. And so our non-centrality parameter here, in other words, this is sort of like the p-value in the alternative distribution, is the difference between the means divided by the standard error, or the standard deviation of the difference, or the standard error. And so if I carry that out, then I get a value here of 0.93. And so in my non-central distribution, or my alternative distribution, here is the beta error rate. So you can see it's pretty high. So if you remember from the standard normal distribution that has a mean of 0 and standard deviation of 1, that about 2 standard deviations from the mean, we have 2.5% of the distribution in each tail. So using the normal distribution, so if we're testing at the 0.05 level, then we're doing what we call a two-sided test. And so we have 2.5% in each tail. In terms of the t-distribution, so we'll just use the t-test here as an example. Our central t-distribution, that is, this is the null distribution. The thing to remember about the sampling distributions, as the sample size gets large, in other words, as it tends to infinity, they all become the normal distribution. And so a t-distribution with a smaller number of subjects or patients, you can see that it's symmetrical. It's thicker in the tails, or in the two sides here, than the normal distribution. But basically, as you increase sample size, it becomes a normal distribution. And so when we do our statistical test, we're going to base it on the null distribution, and we're going to calculate a p-value. And the test statistic that we get is going to be somewhere between minus infinity and plus infinity. So in our case of our example here that we did, where we had 10 in each subject, then our degrees of freedom is n-1 plus n2-1, or 18, because remember we had 10 in each group. Okay, so if we're doing a two-sided test, then our p-value is 0.05, then we would need to compute the area in each tail of the distribution, or 0.05 in each tail. If we're doing just a one-sided test, then we're just going to look at one tail here. Okay, but so for our non-central t-distribution, for 18 degrees of freedom, the t that we calculate equals 2.1. So it would be somewhere over here for a one-tail test, or if we're doing two tails, over in this left-hand tail. Okay, so what we want to do then is we want to look at the probability associated with this non-central t of 2.1. And so with what it turns out then that at 2.1, then our beta error is 0.86, and 1 minus that is our power, which is 0.14, which is pretty low power. In other words, we don't have a really great chance here of rejecting the null hypothesis. Okay. Well, what if we increase the sample size to 100 per group? Okay, then if we recompute our standard error, we get about 1.7, and then our non-centrality parameter here, or our t value for the non-central distribution, is equal to 1.97. And with now we have 198 degrees of freedom, 100 in each group. So the degrees of freedom is 100 minus 1 for group 1 and 100 minus 1 for group 2. And then it turns out for this t value in our non-central distribution of 1.97, the beta probability is 0.17. And so 1 minus beta, which is our power, then turns out to be 0.83, which is a vast improvement from our sample size of just 10. So you can see that that's the way that we want to go to increase power is to increase our sample size rather than increasing the alpha error rate. Okay, so what I'd like to do is to go through some actual formulas here for calculating sample size for some of the more simpler tests. So here's a t-test, two sample t-tests where you have independent groups. And so our n is equal to this ratio here. So what are these components? Well, sigma squared is the within group variance, or that's the standard deviation squared of the two groups. And we can calculate that. Z sub alpha over 2. So the alpha over 2 here, so if alpha is 0.05, then divided by 2 is 0.025. So this is our our score from the central t distribution, or z. Usually the z distribution is used, and then the beta here refers to our non-central distribution. So it so the z score for a two-sided alpha at 0.05 is equal to about 2 or 1.96. The z score for the beta error rate is 0.84 for a beta error rate of 0.2 or a power of 0.8. And then the delta squared here is the effect size. So this is the difference in this case means that you would want to see between the two groups. So all of the other formulas I'm going to show you are essentially the same as this, although they're a little bit different depending on what depending on the statistical tests that we're using. So the numerator is going to be our central and non-central distributions, measure variability, and then the denominator is going to be some form of our effect size. So what if we have paired or repeated measures rather than independent data? So you can see that what's been added here, all of the other things here are the same, the sigma squared, z alpha over 2, the z sub beta. But what we've added here is 1 minus rho, where rho is the correlation between the paired measurements. And then K is the number of repeated measurements. S squared is the variance of the correlated data. And then again, the delta squared is our effect size. So you can see it's basically the same kind of formula, except now we need to add primarily the correlation between our paired or repeated measurements. So, okay, so what if we have analysis of covariance? That is, particularly in a non-randomized study, there might be a variable, or maybe more than one variable, that might be a confounding variable in our results. So we want to take that into account. So how do we do analysis of covariance? Well, it's actually pretty simple. You just calculate the n you would for a regular analysis of variance, or in this case, this is just a t-test and a comparison between two groups. And so what we're going to add is a covariate. And so our new sample size is going to be what we've calculated here times 1 minus rho, or the correlation between the outcome variable and the covariate. And if you work some examples here, you can see that the smaller the correlation, the larger the n that you're going to need. So here is a one-sided superiority test for independent proportions. And so what we've added here in the denominator, in the numerator, is P1 and P2, where these are the proportions in group 1 of whatever the outcome, whatever that we're looking at, which is a yes, no, either or. And so we have our central and non-central distributions here as usual. Then we have proportion in group 1 times 1 minus the proportion in group 1, and plus the proportion in group 2 times 1 minus the proportion in group 2. This here, each of these quantities right here, the proportion times 1 minus proportion, that's the variance of a proportion. Or if we take the square root of that, it's the standard deviation. The square root of this is the standard deviation of a proportion. And so in the denominator, again, we have an expected difference in proportions minus some effect size that we want to see, or in this case, a superiority margin. So if we look at time dependent data or time to event data, such as in this case, Cox proportional hazards, you can see now that the denominator involves several quantities we haven't seen here before. So P1 and P2 are the proportion of the total patients in group 1 and group 2, say, for example. So usually these are, you try to get these equal. So the proportions here, if the groups are going to be equal, both be 0.5. And then D is the expected failure rate in the entire sample. And then the effect size that we have here is our hazard rate, or what I've indicated by beta. So that's in the formula for the sample size here, it's the log of beta squared. You can see the denominator here is still the same idea, where you have the effect size, but you have some additional or different quantities or statistics that go in there depending on the statistical test. So I'm not going to go through the formulas here because they get a little more complex, but if we want to, instead of looking at superiority, we want to look at equivalence or non-inferiority, then a hypothesis of equivalence means that there's no difference between groups. And you can't make that conclusion based on a non-significant test. And the same thing is true of non-inferiority, where you want to show that a treatment group is no worse than the standard of care or the placebo or whatever the comparison group is. So in both of these cases, what you have to do is specify a margin of equivalence. And so for equivalence, if we wanted 10% to be our margin, then we would look at plus or minus 5% on either side of our expected test statistic. For non-inferiority, then that's just one-sided. In other words, you don't really care if your new treatment was better than the standard of care. You just want to show that it's not any worse. And so again, you have to specify a margin, which might be 5% or 10% or whatever you think is the important margin. So it turns out that you need more N to demonstrate equivalence rather than superiority or non-inferiority. But in either case, whether you're doing equivalence or non-inferiority, the smaller the margin, the larger the sample size you're going to need. Okay, so then another sort of common analysis you see particularly in randomized trials that extend for a longer period of time, like 2, 3, 4, 5 years, or maybe even more. And that is that we want to do an interim analysis, or that is we want to take one more look at the data before we get to the end of the study. And so what we have to do is determine how we want to spend our alpha error. And so the way that this is done, and my example here isn't how it's actually done, it just illustrates the concept. So at your first analysis, we'll set our alpha error rate at 0.001. And then at the second or the last analysis, we'll set it at 0.049 so that these add up to 0.05 if that's your alpha error rate that you want to look at. But that's the basic concept behind group sequential designs, where you have more than one analysis. And so what you do in this is you develop stopping rules. That is, can you stop the study before you get to the end of the study? And so here's an example of the way that it's typically illustrated, is that you have the areas here. If this is your test statistic score, if you start out here with your first analysis, your first interim analysis, then we have the second one, then we have a third one, and then at the end here is our last analysis. So in this example here, we're going to do 3 interim analyses, or take 3 looks at the data before we get to the end of the study. And so what we're going to do is we're going to plot our test statistic, and remember that we have set up our error rate here so that it's small, or we need a large difference in the test statistic to begin with, and it gets somewhat smaller as we yes, gets smaller as we head towards the end of the study. So, for example, let's say that our tests look like that. Our first test here is not significant. Our second test here is also not significant. We're still in the continue region here. But at our third analysis, it turns out that we achieve statistical significance. So at that point, at the third interim analysis, we can reject the null hypothesis. And so we then don't continue with the study. We make our decision here to reject the null hypothesis. On the other hand, if it turns out that our statistical tests look like this, where it's not significant, and then we cross over into the this area here, where we're going to accept the null hypothesis, or we're going to fail to reject. So at our third interim analysis here, we make that decision, and we then can stop the study, because there's, the way we've set it up, there's no hope of achieving statistical significance, even if we get to the fourth and last interim analysis. Okay. Then some designs, instead of randomizing patients, we randomize clusters. So when we do this, then the cluster is the unit of analysis, not individual patients. And so power in this case is a function of the number of clusters. It's also a function of the size of the clusters, and then what's known as the interclass correlation coefficient, the ICC, within the clusters. And basically what that is we assume, because the individuals or the subjects within a cluster are related somehow, then there's potentially correlation between among the data of those individuals. And so if our cluster here might be hospitals, might be providers, however many number of clusters we have, and then the cluster size along with the correlation within the same cluster, the larger the sample size is going to need to be, the more clusters we have and the higher the correlation among subjects. So you can see that there's several things to play with here in terms of determining your sample size, the number of clusters, and the cluster size primarily. If it can be shown that the interclass correlation is small, really small, near zero, then you can ignore that. But that's an analysis determining not just how many patients you need, but how many clusters you need in your study. Okay, so let me then sort of finish up here talking about the information that we need to get a sample size. So, and this is information that some is going to be supplied by the investigator or the investigators. So obviously the study design, your research hypothesis, that as a statistician, I would need to know that, or if whoever your statistician is, they're going to need to know your study design. Then we also are going to need to know the type 1 and type 2 error rates. Now, the type 1 error rate, 0.05, is the standard that's used almost universally in any kind of study. The type 2 error rate, however, can vary. Often what is used is 0.2, which means that that's 80% power, 1 minus 0.2. However, sometimes, particularly if you have a study that's being funded, say like by the NIH, they're going to require higher power. So maybe you're going to need to set the beta error smaller, like 0.15 or 0.1. And so beta 0.1 means that you have 90% power. And as you would expect, the greater the power, the more patients or subjects you're going to need. And so the other thing that really needs to be supplied by the investigator is, what is the difference that you're interested in? What is the difference in proportions or means or odds ratios, hazard ratios? And so along with that, I would need, or your statistician would need to know the variance of the difference. Now that might not be so easy to come up with, but if you are getting your data for your information from published studies, we can probably figure this out. So additional information that we need if you have a paired data study or repeated measures, or you're looking at analysis of covariance, then we'll need to know the correlation. The larger the correlation, the smaller the sample size, or the smaller the correlation, the larger the sample size you need. This is often unknown, and if you don't know it, then what you want to do is go with a smaller correlation. And typically, if we don't know that, I go with something like a 0.2, a correlation of 0.2 between the paired data or between the outcome and the covariate. And then we would need to know the ICC for cluster randomized designs. But again, this may not be known unless you have a previous study that calculated that as an estimate. So again, we might use a correlation that's might be reasonable. For some study, like if you're doing educational research and you're studying classrooms, you're comparing classrooms as your unit of analysis, then in that situation, the ICC actually turns out to be pretty high. For medical research, say patients coming from different hospitals, where hospital is the unit of randomization, then it turns out that the interclass correlation is usually not so high. So for time to event analyses, in addition to what we mentioned before, primarily the hazard rate or the difference you want to see, I would need to know the accrual time. In other words, how long are you going to enroll patients for? And then what is your follow-up time? How long are you going to, follow these patients? And then for Cox regression, to calculate sample size, I would need some idea what the overall event rate is. And a couple of other things that come up in determining sample size is dropout rate. And almost regardless of what your design is, usually people estimate some dropout rate. And so if this is like 10% or 20%, then we take that into account in terms of enrollment. So if we calculate based on the dropout rate, what you're going to need to achieve the number of subjects you needed in your power analysis, then we'll enroll more patients or more subjects to account for dropout. And then the same sort of thing is true for crossover. That is a situation where it's possible that they might be randomly assigned to one treatment, but just because of the nature of the disease or whatever it is you're treating, they end up getting the other treatment instead or in addition to. So if we know that, then that might help us to better estimate how many patients or subjects we're going to need. Okay, so then let me talk about abusing power. And this happens quite a bit. And so the most common one is that we're going to inflate the effect size. In other words, the bigger the effect size, the fewer subjects you're going to need. And so in order to get a reasonable number of subjects, or the number of subjects that you can afford, they make the effect size really large. However, that's really not a good idea. You need to base it on a meaningful difference or a clinically significant difference, rather than making it so big that you don't need as many subjects, as many patients. And this happens, I've seen this quite a bit particularly in the medical literature. And sometimes you'll see effect sizes of like 35, 50%. Well, those are probably not realistic, or they're not they're not suggested because they are what you would expect in the population that you're interested in, but they've been chosen to decrease the sample size. Then putting a large correlation for paired data or for analysis of variance. And so, as I suggested when we looked at that too, if we don't know what the correlation between paired data is, then we should probably make the correlation smaller. Then another one that hasn't been done as much, although I still see it once in a while, and particularly if I see it sometimes from editors of journals and from other reviewers, is doing a post hoc power analysis if you get non-significant results. Some years ago, quite a few years ago, when the institution I was at, I did a lot of statistics for basic scientists. And in some of their journals, they actually required that you do a post hoc analysis if you got non-significant results. However, a power analysis after you've done your study really has no meaning, because presumably what you want to say is that, well, if we had an additional 50 subjects or 50 patients, we would have gotten statistical significance. Well, you can't say that because your study is over with, and adding subjects is going to change the parameters of your estimate. So the only thing that you can really use your non-significant results for is to do a power analysis for another study or for a future study. And in the references, there's a really neat, although it's a little more technical, article on doing post hoc power analyses. So one thing that I want to mention, and it's probably obvious to everyone, is that you have a limited budget in doing your study. So it turns out that sample size is dependent really on cost or the feasibility of getting a number of subjects or a certain number of subjects. So usually when I do power and sample size estimates, I'll start out by asking, how many patients can you afford? In other words, what's sort of the upper limit on the sample size here? And then, as I mentioned before, there are some unknown parameters like correlations that go into calculating sample size that we might not know, but there are ways of handling that. And then finally, well, actually, one more thing is if you do a pilot study, the purpose of a pilot study is to estimate the effect size and the variability. So in this case, a power analysis isn't particularly relevant. However, I've seen this, it's often required. If you have a funding agency, they want you to do a power analysis, but I think they don't quite make the connection here of what you're doing with what a power analysis is supposed to do, that we're doing the pilot study because we want to find out. We want to get an estimate of the effect size. So if you have to do it, then there's a way we can do that with some meaningful or theoretical effect size, but we'll put it in the context of a pilot study. And if you do a pilot study, then it's recommended that you have between 20 and 30 subjects per group. And if it turns out that you get statistical significance with your pilot study, you can't claim, you can't use that as evidence of a difference, because when you get statistical significance with small samples, it's often spurious. And then the last thing here, if you really don't know anything, you're basically breaking new ground, then what can we do as far as estimating sample size? So what I do in this case is we'll take a range of effect sizes that are reasonable based on your particular study. And then for those, and then we'll make some estimation too of what the variance might be. And so I'll calculate the sample size per group for 80%, 85%, and 90% power, and how many you would need. And so because budgets are limited, the number of patients you get is dependent on your budget. Then you can sort of make what's kind of a best educated guess on what's a reasonable effect size and what's a reasonable number that you can afford, and what power level we could do that at. So there's software where you can do power and sample size calculations. There's some online, although those tend to be somewhat basic, like for t-test or chi-squares. There are sample size, power and sample size, and different statistical packages. Two that are primarily used, that are standalone for sample size only, are Inquiry and PASS. And if you're interested in looking at those, if you don't have access to them, the websites. And I have a couple references here on sample size calculations. And then the last one is from the American statistician several years ago on the fallacy of power calculations for data analysis. So with that, I think we're almost out of time. So let me take a look here. Yeah, so for a margin of equivalence, right, you would have to base that on whatever statistic, like the median or the mean, within, and so you would set bounds around that to calculate the sample size. Okay, another one here. When basing an effect size on previously collected pilot data, should the mean of the pilot sample measurements be used, or is it better practice to take the confidence interval into account? I think most people just take the mean, but you can use the confidence interval to get sort of a range of possibilities and calculate the sort of the lower bound and upper bound of what a mean might be. Let's see here. Oh, okay. So there was a question about both sample distributions look like the normal distributions. Yes, yeah, I just basically, for illustration, calculated a symmetric distribution that sort of looked like the normal distribution. As I mentioned, the sampling distributions, as sample size tends to infinity, they become the normal distribution. So like the chi-square distribution for small sample size is skewed to the right. So it's yeah, just for an example here, I'm not actually using a particular distribution. I use the T just because it sort of looks like the normal distribution. It's possible to show us how to calculate the sample size using power for all scenarios using SAS. Okay, I can look that up and do a couple examples. I use Stata for if I have a sample size that's calculation that's fairly straightforward. The ones to use for really that have from simple to really complex designs are pass and inquiry, and they have really pretty good descriptions along with them. And let's see, recommendations for some good books, software, or resources. I'll look up a more find a more current book and send that along. And some good online sites for simple power calculations. I would just Google, statistical power or something like that, and see what comes up. I don't really use online sites, so I'm not really up on what is which ones are really good and which ones are not. And I think maybe one more. Okay, so differentiate between covariance and correlation between. So a covariance is the variation between paired data. In other words, measurements from the same individual. So these can be like repeated measurements, or they can be data that's correlated. So for the ANOVA or ANCOVA, we'd have data sets that are, or we would have data that are outcome data, and then some covariate, like age, maybe that would be correlated with the outcome. And so that's that's what we mean by covariance. And then the correlation between them is just the standardized covariance between them. Okay, so I want to thank you for your time. And as I said at the beginning, this has been recorded, and the folks at Georgetown will send that out to where it's available. And the slides will be sent out to everyone who's been registered. So again, thank you for your time, and I hope you have a good day and a good weekend.